The movement of heat around the globe is one of the most critical components of Earth's climate system. The driving force behind this process is the sun.
We know the equators are warm. At the equator, you get more heat than the Earth can absorb. At the poles, you get less heat than it is capable of absorbing. So you have an excess of heat at the equator, a deficit at the poles, and the atmosphere is constantly trying to get rid of that difference. This leads to atmospheric circulations.
The circuits of air that move as part of the circulation process are known as cells.
An atmospheric circulation cell, and there are many of them, is generally an overturning.
An atmospheric circulation cell is where you have air rising in one place, and to replace that air that's rising, air has to come from someplace else. If you imagine a room, you have a radiator on one side of the room and windows on the other. The warm air by the radiator is rising, cool air is sinking by the window, and it comes across the room and rises back through the radiator, and you get an atmospheric cell.
The most basic of all of these cells is the Hadley cell. And the Hadley cell is the sort of a universal flowing of air towards the equator and rising and flowing back towards higher latitudes.
And the Hadley cell is the idea that you would have rising air at the equator and sinking air at the poles, and that you'd get this circulation that would move warm air toward the poles and cool air from the poles back to the equator.
While the initial motion of these cells may be driven first by temperature and then by pressure gradients, their precise movement is also influenced by the rotation of Earth itself. It is this rotation which deflects the path of any moving object, including air or water, from its initial course. This deflection was examined in detail in the 1830s by a French scientist named Gaspard Gustave de Coriolis.
The Coriolis force is perhaps the most feared concept in weather forecasting. All of us who teach always shake our heads about trying to explain this, and it's not simple. It is the issue that when you see air flowing on the surface of the Earth in the northern hemisphere, it appears to turn to the right. So this is called the Coriolis Effect. We talk about a Coriolis force, which there must be a force present making that happen, but it is an apparent force, because we simply have to put it in mathematically to make this turning happen. Now, in simple terms, imagine you're in an airplane in Chicago, and you're going to fly due south to Dallas. You fly due south for 3 hours to Dallas, but when you get there, Dallas isn't there anymore. Dallas has moved to the east 1/8 of the way around the Earth, if we rotate every 24 hours. And so if you look at the path of the airplane relative to the Earth, it appears as if it has been deflected to the right.
The Coriolis effect is an apparent force that arises when an object that is moving is viewed in a reference frame that is rotating. And a good example of this occurs on a merry-go-round, which is a rotating reference frame.
If you are on a merry-go-round and you're sitting on one side and your brother's sitting on the other side, you try and throw the ball to your brother, you'll miss him to his left because the ball will be deflected to the right. The reason is that your angular momentum on this rotating sphere is moving the ball to the right, and your brother is going to the left, and when you throw it at him, the ball appears to be deflected to the right.
The tennis ball you were playing catch with would go in a beautiful arc of a circle. It wouldn't go straight. And, of course, that tennis ball is going straight for an observer who's not on the merry-go-round, but you don't know that.
I think the one thing one should do is think of a planet where there was no rotation. Then, except for inhomogeneities, mountain ranges or oceans and so on, all the flows will be between the equator directly to the pole. They'd be all north-south, very, very boring. And so what we have, and as the equator would heat up, say during the summertime or some stage, this Hadley circulation would just get faster and faster and transport all the heat.
If there were no Coriolis force, it would descend by the pole. But instead, it rises by the equator, it starts toward the pole, and then it is deflected to the right. And eventually, it never gets to the pole. It only gets to about 30 degrees north, where it begins to descend because it's cooled. And eventually, it returns near the surface, where it is also deflected to the right. And this causes the trade winds that blow in the Caribbean and over the islands in the Pacific and across Africa. And they, of course, were the winds that allowed the early traders to sail along the equator and move to different continents. So without the Coriolis force, we would not have the circular weather that we get today, and the patterns that we're used to seeing would not exist.
Of these patterns, the Hadley cell is generally considered to be the most basic. But there are other atmospheric circulation patterns as well.
You also get cells in the east-west direction, which are called Walker cells, named after Sir Gilbert Walker, who was the person who first did some seminal work in the El Nino Southern Oscillation thing 70 or 80 years ago. And this is the overturning along the equator between regions of very, very warm sea surface temperature, like the western Pacific Ocean, and cooler regions in the eastern Pacific Ocean, where one gets overturnings again. And so these atmospheric cells are extremely important.
Our prevailing winds in the United States are typically from west to east. Now, that descending air then runs into air coming from the pole that is trying to get to the equator because of the difference between the cold air at the pole and the warm air at the equator, and it begins to rise. So in the middle of the Earth, between 30 degrees north and 60 degrees north, you have what's called the ferrule cell, descending air about 30 degrees north, ascending air at about 60 degrees north, and then you have the polar cell, which is air descending over the pole and rising at about 60 degrees north.
One of the circulation zones that scientists are especially intrigued by is located near the equator. It's known as the ITCZ.
ITCZ means Intertropical Convergence Zone. When one looks at a satellite picture where all the cloudiness is averaged over a long period of time, you tend to see around the equator, just to the north or just to the south, depending on the season, a band of cloudiness. And this is referred to as the ITCZ. And it's generally thought to be the confluence region, or the region where the trade winds from the northern hemisphere meet the trade winds from the southern hemisphere. And in the simplest sense, one can think of that as that's the rising part of the Hadley circulation. Now, these trade winds have been traveling over very, very warm air, and as they come together and are forced to rise, one gets the release of latent heat. And this, of course, heats the atmosphere and tends to draw more air into that region. So you finish up with a very strong circulation cell. So the ITCZ is a very turbulent part of the atmosphere, a very, very important part of the atmosphere.
If you're sailing, you can see it very clearly. Recently, I flew from Atlanta to South Africa, and I could immediately tell when I was over the ITCZ. And this zone causes rain, very persistent rain, and it is the feature that saves so many countries who need rain and have dry periods and wet periods. The ITCZ moves northward in our summer and southward in our winter. And for example, Kenya, Niger, and Africa have the rainy season from May through September or October, as the ITCZ is over them and causing all this convection.